Alright class, today we're in section 10.5, which is segment lengths and circles. We're going to be taking a look at a couple of theorems today and some vocabulary too, just to make sure that we understand when there's segments within our circles, what happens with them and what kind of special relationships exist. The first theorem we're going to be looking at, 10.15, it says if two chords, so notice I've got two chords that are intersecting in the interior of a circle. So I have two chords intersecting somewhere inside the circle. We've looked at what happens with their angle measures, but now we're going to look at the actual length of the segments. It says the product, so we're going to be multiplying the lengths of the segments of one chord. So if I look at one chord, it's being divided into two segments. So the lengths of this segment here and the length of this segment here, that product. So CE times ED is equal to the product of the lengths of the segments of the other chord. So I could say that it would equal AE times EB. Now, the reasoning that this works, because of course every theorem can be proven, the reason that this works is because what we're really forming here, if I go ahead and connect these segments, as I've got two similar triangles. I know that they're similar because I know, like for example, these two angles right here are both intercepting the same arc. So I know that these two angle measures are the same. I also have some vertical angles I could talk about, or I could do the same thing with angle A and angle D, talking about they're intercepting the same arc as well. So we know that these two triangles are similar. So if I look at their corresponding parts, I could say that CE corresponds to EB, and I know that also AE is corresponding to ED. Those are corresponding parts, and if you cross multiplied, you'd see that you're going to take CE times ED would equal our AE times EB. So you get the same thing. The theorem is just a nice shortcut way to get there. So when you've got two chords that intersect inside of the circle, the product of the lengths of one chord will equal the product of the lengths of the other chord. Alright, now the vocabulary that we're going to take a look at, we've seen the words tangent and secant before. The difference is we've talked about these as lines that continue. A tangent segment is just a segment that is tangent to a circle at an endpoint. So we know that a tangent segment is going to have an endpoint that's on the circle that is the point of tangency, and it's a segment, so it's going to have another endpoint. So this right here would be an example of a tangent segment. Now, a secant segment would be talking about a segment, again, that intersects our circle in 2 points still, because it is a secant, but one of those points is going to be an endpoint of the segment. So one of our places where it's intersecting the circle is an endpoint, and its other point is going to be somewhere outside of the circle. So it's not just a chord. It does continue, but it does have an endpoint at somewhere else. So this entire piece right here would be considered a secant segment. Now, the external segment is going to be part of a secant segment that's not inside the circle. It's just outside. It's external. So this part, this segment PQ right here, that would be an external segment. Alright, we're going to be using that vocabulary in our next couple of theorems. Alright, this next theorem says that if we have two secant segments, so notice these are two segments, they intersect our circle at 2 points, one of those points being the endpoint of each one of those segments, that share the same endpoint outside of the circle. So they have point E in common. When this happens, the product of the length of one secant segment and the length of its external segment. So let's take a look at that. The length of one secant segment, EB, and the product of that and its external segment, EA, equals the product, so again we're going to be multiplying the length of the other secant segment and the length of its external segment. So the product in this case of ED, that whole secant segment, and its external segment, EC. Anytime you've got a point outside of the circle, we've looked at angle measures. This is talking about segment lengths, though. It says, again, the whole secant segment and its external segment, those two parts, that product, is equal to the whole other secant segment and its external segment. So just some relationships that exist with those segments in a circle. This last theorem that we're going to talk about today is very similar, but notice here I don't have two secant segments. I have a tangent segment and one secant segment. So if we have a secant segment and a tangent segment that share an endpoint outside of the circle, so they have this point E in common, then the product of the length of the secant segment and the length of its external segment, so it's starting off just like the last one, the whole secant segment, ED, and its external segment, EC, that product equals the square of the length of the tangent segment. Notice for the tangent segment, this is entirely outside of the circle. So I can't talk about the tangent segment and its external part. So it's the same thing both times. We're just going to say it's EA squared, or EA times another EA.